Hi everyone, today me, Shubham Rishi, and Ritul Joshi, both being part of Group 7, will be presenting our class presentation for our course COM 381, that is Introduction to Machine Learning, on the topic Feature Mining for Image Classification. Throughout the presentation, we will only be covering some certain key aspects of the research paper. So, what will be our agenda? Well, throughout this presentation, we will cover these following topics: a brief introduction and a bit detail about features and supervised learning. Then we will talk about computational complexity of a feature. After that, we will talk about feature mining, which will be followed by feature mining strategies. And then we will present the result, observation, which will be followed by the conclusion of the research paper. So let's start with the introduction. Feature engineering. Well, it refers to the process of using domain knowledge to select and transform the most relevant variable from raw data when creating a predictive model using machine learning or statistic modeling. Feature designing is a part of feature engineering and is a critical issue in the computer vision and machine learning since it influences a vision system performance. Now, if we talk about the second point, that is feature extraction. Feature extraction is essentially a dimensionality reduction problem with the goal of finding meaningful projections of the original data vector. Now, everyone's wondering like what is a good feature? Well, a good feature should be informative. The more information, the better to know categorize it. Second, it should be invariant to noise or a given set of transformation, and it should be fast to compute. More faster, more better. Well, there are different ways like mean, variance, edges, gradients, filter responses, color features, geometrical features, etc., using which we can extract feature from an image. Feature mining? Well, feature mining refers to the task of organizing and exploring large, possibly infinite spaces of heterogeneous features. The aim of the feature mining is to automatically discover meaningful features and to alleviate burden of manual feature design. That's why we use machines. The paper talked about feature mining paradigm and the concept of data-driven feature space, and also a principled approach for dealing with features with varying computational demands. In feature mining, the goal is not to pick a subset of features from a larger set, but to rather explore and model the entire space of features. Feature mining and feature selections are in sense of compatibility. So, features and supervised learning. Now, the first topic covered in the paper was about feature and supervised learning. If you talk about supervised learning, then it is a subcategory of machine learning and artificial intelligence. It is defined by its use of labeled dataset to train algorithms that is used to classify data or predict outcome accurately. We only look for accuracy. So we should note that in supervised learning, the goal is to develop a function that maps input to desired outputs and then generalize well to new data. Such a function can be learned directly from the data in the representation which it is given. However, the frequently makes problem intractable, either because the chosen classifier lacks the representational power to encode the function or because the amount of training data required is prohibited. So those are just a problem of supervised learning. Now, if you talk about discrete AdaBoost, so AdaBoost combine a subset of the mind feature into the final classifier. We will discuss about AdaBoost in brief detail in the next slide. So we'll continue with computational complexity of a feature. Well, in the computational complexity of a feature, a simple extension was applied to the AdaBoost to deal with heterogeneous computational complexity. The key use of this is to introduce the notion of partial feature. This thing is intuitive with the nature of greedy algorithm, but makes ADA boost procedure way more efficient. So discrete ADA boost, we are back to this. Now the diagram here gives a brief description of our ADA boost algorithm, which can be understood as following. The given n labeled training example xi and yi just up in here with a pre-assigned range set and with an initial distribution di, which is this, and the distribution di is right here. Now what AdaBoost does is that it combines a number of weak classifier, which we denote as HT right here, to learn a strong classifier HX, which is the product up here. The training error is bounded by the equation ET. We have shown ET up here, and where the T is the number of weak classifiers. The VC dimension of a classifier H, which is VCH, can be used to derive a loose upper bound on the expected test error of H. Well, in this algorithm, it should be noted that the test error does not depend on the number of weak classifier. So, what would be the tactics of like training the ADA boost? Well, the tactic should be like first, increase the number of training samples. Second, reduce the training example. And third, reduce the complexity of the weak classifier, and hence you got the best ADA boost up here. So let's hop on to the next topic, which is feature mining. So if we talk about feature mining, our main goal is to minimize human efforts needed to explore and organize the vast space of possible feature for image classification. That's why we are using machine learning to reduce the work done by the human, make the machine capable of doing the stuff. So let's hop on to the first thing, which is what is parameterized feature. Well, parameterized feature space is a feature space which for a given class of feature is simply a human design space of features where each feature is an element of a function with x with a set range of elements. In this, we assume real valued features are transformed to binary by the process of thresholding. So now if we talk about the challenges for parameterized feature, then we can say that we have no notation of where to look in the space. Don't know where the feature is in the space because, yeah, no idea. Second, we lack a measure of distance between features because we don't have any notation as specified in the first. So now let's see data-driven features. Data-driven feature space represent each feature independently of its parameterization. It is categorized by its response to the data. So now I'll let Ritul to take over the other part of the presentation.
There are experimental results on three datasets. The first is the MIT CBCL phase dataset. Although aligned frontal phase detection has essentially been solved, this simple dataset is still useful for comparative studies. Recently, pedestrian detection has received much attention. Specifically, there has been much interest in designing more effective features for tasks. The goal was to put little effort into designing P, yet P must be large and complex enough to represent diverse patterns. The first to compute Haar's wavelets are widely used in the community. Each Haar wavelet is computed by summing the pixels of 2 to 4 weighted rectangles. Here, here is where Haar's wavelets are generally introduced, which are likely like the original Haars, but with arbitrary configuration and number of rectangles. Even for a 50 by 50 image batch, there are 10 raised to power 6 configuration for single rectangle. With multiple rectangles per Haar, P becomes quite vast. These features are capable of representing some fairly interesting patterns. There are a number of basic strategies that have been implemented. The first one is SYST, which is systematically designed for face detection. The second one is RAND, randomly sampled features from P. The third one is GOOD, the space is mined for informative features. Random features are sampled from P and the most informative according to Z are kept. Additionally, steepest descent search in P is used to define the best features. The fourth one is COMP. The space is mined for informative, complementary features. Here we exploit a metric on F and use a simple online clustering algorithm where each cluster is a sphere of fixed size radius. Let Q denote the current set of selected features. Features are sampled randomly from P. Each new feature can 1. Become a new cluster center, second, replace an existing cluster centers, or third, be deemed as redundant. The first set of experiments are meant to compare systematically designed features and various feature mining strategies. Results on the three datasets are shown. The ordering of performance of the feature mining strategies on each dataset is RAND, which is smaller than GOOD, which is smaller than COMP, which is smaller than COMP plus SRCH, which is expected. The interesting thing to see was how near COMP was to COMP plus SRCH graph. Coupled with the worst performance of GOOD, this serves as the verification that metric over F works well. Although GOOD plus SRCH often did not work as well since the candidate feature for search were not diverse enough. RAND plus SRCH, when used with a lot of random features and deep search, can be seen as a brute force method for exploring F during each stage of boosting. In terms of performance, RAND plus SRCH with a large number of features did not greatly outperform COMP plus SRCH. A simple experiment was performed with two different classes of features. The first, hours computed over the original image, and the second, hours computed over the gradient magnitude image. It turns out that using just n mixed features for the both type is better than either 2n features of types or one of type 1 or 2n features of type 2. It is interesting to observe the asymptotic features performance of a train boost classifiers as the number of weak classifiers increase for the various feature mining strategies. A cascaded classifier was trained with 20 levels and features mined from P. Using an identical training, bootstrapping, and testing setup, we applied two feature mining strategies. The first one was RAND plus SRCH plus TC with a small number of initial features, and the second one was RAND plus TC with a very large number of candidates, giving similar results. In both the cases, Using complementary channels and TC were essential. For, for low false positives, our results essentially match the best reported results obtained using the histogram of gradient feature designed specifically for this data. The aim of the work was to lay out a general framework for feature mining, grounding it in theory, and supporting it with experiments. Feature mining is meant to reduce the effort and expertise necessary for feature design and ultimately serve a foundation for systems that can outperform those based on manually designed features.
Thanks, Ritul. And now this all concludes our presentation. I hope that you liked it, and if there is any question, we would be happy to answer it. Thank you very much for watching this video till the end.